Hello everyone. So in the first lecture we have seen what is simple harmonic motion. Then we found out the equation of motion of simple harmonic oscillation. Then we found out the solution of equation of the motion, and then in the last video we interpreted the solution of simple harmonic motion. Okay, now in this lecture, or particularly in this video, we will see why we study simple harmonic motion in detail. Okay, now you may say, well, we see simple harmonic motion all around us. So there are many examples of simple harmonic motion. The swinging pendulum is an example of that. So you may say that is why we study simple harmonic motion, but actually the reason is a little more vast than you think. Okay, so a lot of complicated motion actually can be approximated to simple harmonic motion. That's why we study simple harmonic motion in this much detail. So let us find out when we can approximate a complicated motion as a simple harmonic motion. Now, before starting the approximations, let us have a brief review of conservative forces. So do you remember how do we define conservative force? Okay, so what is actually conservative force? Well, a conservative force is a force which obeys this simple equation. That is the closed integral of force dotted with dr is equal to 0. Now, what does it mean? Well, it means that if you start from a certain point and then if you move about against this force F and come back to the same point, the total work done, which is denoted by this expression, is 0. Okay, so that means the force is not dependent on the path that you take. This is what we call an example of a conservative force. Now, we can actually write down a conservative force by using the potential due to which the force is there, right? The general expression is actually a vector equal to minus the divergence of the potential. Okay, so this is the expression. Now, of course, you see this is in the case of 3 dimensions. Now, if we just write down for 1 dimension, we can write down these equations as, well, the first one as a closed integral of f dx equal to 0, and the second one as force F to be equal to minus dt x of the potential. Okay, now from this equation actually we can define the potential difference like, say, delta U, the potential difference, to be equal to integral of f dx with a minus sign. Now for SHM, the simple harmonic motion, we can define the potential difference delta U to be equal to what? Well, you can see we have to integrate the force in case of the simple harmonic motion, and in case of simple harmonic motion, the restoring force is actually equal to minus kx, right? So we have this equation. So the potential difference here should be minus integration of minus kx, right? Okay, so you see it will give us half kx squared. Okay, now if you plot the potential difference in terms of x, okay, what do you get? Well, let us plot the potential rather than the potential difference. Okay, so this is the potential difference, and you know that we can set the potential at any point to be equal to 0. So this potential difference can be written as, you know, simply some potential minus the potential at the initial point, which we can always set to be 0. So this can be considered as a simple potential. So potential will be equal to minus half kx squared. Okay, now if we plot this potential with x, what should we get? Well, you see it is a parabolic equation, so we should get a diagram like this, okay, for the potential. Okay, so now what is force in this graph? Well, as you can see, force is defined as minus the ddx of u. So that means the force is actually the slope of this curve with a negative sign. Okay, so here at this point, you see the slope is steeper, so that means the force is higher. And here near to the point of equilibrium, you see the slope is flatter, right? So that means the force is smaller in this region. Okay, so we have seen that the potential of simple harmonic motion takes this parabolic form. Okay, now what happens if we have some kind of potential which is not parabolic in shape but some other complicated shape, but it has to be a well-behaved function if we want to approximate that harmonic motion. Okay, so let us now consider a complicated potential function. Now let us consider a somewhat complicated potential than the simple harmonic motion. Okay, so let's say we have a potential which is given by a plot. So let's say in the y-axis we have ux, the potential, and the x-axis we have the displacement x. Okay, so let's say the potential has the form like this, so maybe like this. Okay, so let's say this is the form of the potential ux. Now this point here, this one here, the function is at local minima, so let's call this point x0. So this is our local minima. Okay, now what should be the form of ux? Well, we can actually find that out by Taylor expanding this potential in terms of this point x0. Okay, so those of you who are not familiar with what Taylor expansion is, I would suggest you to watch a video which I will provide a link of that actually gives a very good introduction to Taylor series. Okay, so I hope that you will watch that one. Okay, so now let's expand this potential by using Taylor series. So the first term is u of x0. x0 is this point, right? So this is just the function evaluated at the point x0. Then the second term is ddx of u evaluated at x0 times x minus x0. So this is just a number. Okay, and we have x minus x0 multiplied with this thing. The next term is 1 over factorial 2 d squared u ddx squared evaluated at x0 times x minus x0 whole squared. Okay, the next term 1 over 3 factorial d cubed u ddx cubed evaluated at x naught, x minus x naught whole cubed. Again, all these things here is just a number, okay? And this will go on and on and on. So this is how you expand the potential with respect to some point x naught by using Taylor series, okay? Now, if I ask you what should be the form of the force fx, well, you should be able to find that out as well, because a force a conservative force can be expressed as minus ddx of the potential, right, in one dimensions. So we'll have all these things differentiated with respect to x, okay? So now if you differentiate this quantity, well, it's just a constant, so it should return you 0. Then if you differentiate this quantity, this is just a constant times, if you differentiate this, you should only get 1. So minus times this constant, okay? So the first term will be minus ddx of u evaluated at x naught, okay? So this is the thing. Now if you differentiate this quantity, what should you get? Well, again, this minus sign here, and if you differentiate this thing, it should return 2 times x minus x naught, and you see that 2 and this 2 will cancel each other out, so we'll have again d squared u ddx squared evaluated at x naught times just its derivative x minus x naught. The 2 already cancelled out, right? So what should be the next term? Well, if you differentiate this 3 will come out in front and will cancel with 3 here, so we'll have only 1 over 2 here. So 1 over 2 times, again, this is just a constant, so ddu of ddu dx cubed evaluated at x naught times what? Times this thing differentiated, already 3 cancelled out, so we'll have x minus x naught whole squared. And this thing will also go on like this. Okay, so now that we have the forms of the potential and the force for this well-behaved, complicated looking potential, let us now evaluate something, right? Okay, you see this is x naught, so this is the local minima. So you see at this point the slope with respect to x should be 0, right? You see the line, the tangent is flat here. So what you can say that this term, which is the slope evaluated at x naught, is equal to 0. So we can write down this thing to be equal to 0. And again, this term here as well is the same thing. So this is 0 as well. Okay. So then you are left with all these terms. Now, if we consider a very, very special case, that is x minus x naught is very, very small. So let us consider a case where x minus x naught is very, very small. Okay, so very small. What we can do? Well, if this is very small, we can ignore the higher order terms, right? This thing cubed and power 4, you understand that these things should be very small compared to all these things, right? So we can actually ignore these terms, okay? So if we apply this approximation, we can write down the potential can be approximated to what? U of x naught. This thing is already 0, so we'll have half this thing, that is d squared u of ddx squared evaluated at x naught times x minus x naught whole squared, right? So this will be the form of the potential. Now, what should be the form of the force? Well, you already know that we ignored these terms. Well, so we can ignore these higher order terms. You understand? So it should contain this thing, right? Only this quantity. So we can write down fx approximately equal to what? Minus d squared u dx squared, dx squared evaluated at x naught, x minus x naught. Okay, now have a look at this quantity. Well, this is just a number, you see. It is just the second derivative of the potential evaluated at x naught, so this is just a number. So if we call this a number or a constant, like ddx squared of u evaluated at x naught, let us call it k, then what should be the form of the potential? Well, we can write it down as ux, and if we take this one on the left hand side, ux naught can be written as approximately half times that constant times x minus x naught squared. Okay, and this force can be written as minus kx minus x naught. Okay, so this is the form of the approximated potential and approximated force, right? When we applied this approximation, x minus x naught is very small, right? It is very smaller than 1. We can write down these sort of approximations. Okay, now here we have x minus x naught. So if we you understand that if we define some other coordinate system, we can write it down as some x squared in that coordinate system, right? So this is just a coordinate transformation, so you can write this as half kx squared, right? So it would lead to half kx squared, but here we have potential difference. But again, you should note this, that in case of conservative forces, in most cases except gravity, we only need to know the difference in the potential, not the real potential. Okay, so we can always set the potential at any point to be equal to 0. So maybe we can write down the potential at this point to be equal to 0. Okay, we can set the potential at any arbitrary point to be equal to 0, other than the case of gravity. Okay, so if this is the case, we can write down from this u of x to be equal to, or approximately equal to, some constant half k times x squared after some coordinate transformation, you can say. Okay, so this should be familiar to you. This is just the potential of simple harmonic motion, half kx squared, right? You see, we have approximated this complicated looking potential for very small displacement, okay, to be some kind of simple harmonic motion, you see. And if you see in case of the force as well, we can do that as well. So after some kind of coordinate transformation, we can write down the force F here to be equal to, or approximately equal to, minus k times x. Okay, so these two are equations of simple harmonic motion. So you see here, we haven't started with anything related to simple harmonic motion, right? It was just an arbitrary potential, but you say it was well behaved. That means that we could differentiate it at any point, right? This is required if we want to expand that using Taylor series. Okay, so it was a well behaved complicated looking function, and we expanded it by using Taylor expansion. Okay, and then after applying this approximation, okay, we found out that we can apply for very small region, very small displacement. We can actually approximate this motion, this arbitrary motion, as a simple harmonic motion. So you see, this is why we need to study simple harmonic motion, because we can approximate nearly any well-behaved potential as for some small displacement as a simple harmonic motion.